Hi, in this video I'm just going to give you an example of the different ways to calculate torque. And I'll do the same process, or the same problem 3 different ways and show you that they're all the same. But I have a preference, and if you do the other ones, that's okay. You'll get the same answer. So let's say we have a beam and it's held up by a rope, and there's a sign just like we did with the extended force diagram and attached to the wall. Okay, and then we do the extended force diagram. Okay, you can go look at that video. We've got tension, we've got the weight of the sign, we've got the weight of the beam, and we've got our hinge forces. FHY, FHX. So I'm going to just focus on this tension force. So how would we calculate the torque from the tension force? I'm going to do it 3 different ways. First way, all right, and that's the way I tend to do. It's the parallel force times the distance. So with this, I'm going to just rewrite it. Oh, this marker's dying. It's not going. Okay, so with this one, I've got the tension, and I'm going to assume the pivot point is right here, so there's my pivot point. Now here, what I'm going to want to do is first I draw the radius, that lever arm, so R looks like that, distance from the pivot to where the force acts, and so that's the R piece. Now I want the perpendicular force to R. The tension has 2 components. There's this component and there's this component. Say this is an angle, theta. Okay, which of these 2 components is perpendicular to R? Well, R is like this. That means this is the perpendicular component. I want this side. Is that the sine or the cosine piece in this case? Here's the angle. That's opposite the angle. In this case, what we would end up with is it's the tension times the sine, because that's the opposite, times R. So the torque here would be T sine theta times R. So that's one way to do it. Okay, so for the second method, it's the idea of the perpendicular distance times the force. And this is the true definition of the lever arm, is this perpendicular distance. So for this, what you do is you draw the perpendicular line from the pivot point to the force. So if this force is acting on a line like this, then the perpendicular distance, let's see, perpendicular would be about there, something like that, R perpendicular. Okay, so we have R perpendicular, and that would be perpendicular to the line of the force. So the force acts along this line, we draw that R perpendicular. Now we had TR sine theta before. What do we have here? Well, okay, the force is just the tension, so the force is the tension. R perpendicular. We had this angle before, and so how do we figure this out? Well, that's the angle. My total radius is still here. My total distance is there. I only want the perpendicular component. So if I, oh boy, how can I draw this? Let's see, so that's R. This is R perpendicular, which is the piece that I want, and this is my theta. That's my 90 degrees. Okay, so there's my theta, there's my 90 degrees. So which component of R is this piece, this perpendicular piece? Well, here's my angle, here's my hypotenuse. This is opposite to the angle, so the perpendicular component of R is R sine theta, which means T R sine theta. Same thing as before. So we've got that second way, which is using the perpendicular line of action, sometimes it's called. This is the line of action. And then we've got the perpendicular to the line of action. So that's number 2, same equation. All right, here's number 3, and this is the method that Dr. Hopp uses the most, so if you watch her videos, you'll see this a lot. And again, I don't care which method you use, so long as it's the correct method and you do all the physics correctly. Correct method. One of the correct methods, what am I saying? As long as your physics is good. I don't care which way. So here we have the definition was torque equals Fr sine theta from R to F, which means we need to know the line of R and the line of F. Okay, this is our radius, and I'm going to extend that, just like I extended the force line last time. I'm going to extend that and say this is R. I'm going to go from R to my force, and that's what we're going to have there. This was my angle. Now, this angle here, we've got to be careful. This is a generalized theta. This is a specific theta. So in this case, the force is T. The R is just the R. You'd measure that, put in that. And then we want this angle. And in this case, this angle would be the line minus theta. Remember that? So line is 180 degrees minus theta. So here, the torque would be TR sine 180 minus theta. And if you go back and do your trigonometry stuff, which I had to look up, I have to admit, what you get is TR sine theta. Same thing. So there's 3 different ways. Again, the first way is the way I tend to use. This way is the way that Dr. Hopp tends to use. Use whichever one makes the most sense to you. If you like that line of action and then the perpendicular distance, use that. If you like this method, use that. One of them is likely to make the most sense to you, so use that one. Now my solutions use the first one, but it doesn't mean that that's the only way to do it. So try them. I would suggest trying all 3 methods, or just thinking through all 3 at least and say, oh, that's what works for me. You know, the reason I do the F perpendicular is because that's how my brain thinks about it. It's the perpendicular part of the force that causes a torque. So I'm going to talk about F perpendicular. Maybe you'll like one of these other methods, whatever. So there's 3 examples. Good job.